Hello. Okay, let's begin. I am Maria Andrade. I am from Federal University of Sergipe, Brazil. I am very honored to stay here. First time at the ICTP. This is a good pleasure to stay here. So, and I would like to thanks a lot people and especially research in Paris because this is partner from me. And if during my mini course, if you have some question, please open your microphone and ask me, okay? Because I don't see if you put, for example, in the chat, I write in the blackboard and I pass the slide, okay? And so today we talk, this mini course is about free boundary, constant mean, curvature, hypersurface. In fact, we talk about free boundary, constant mean, curvature, hypersurface in the ball, okay? So what's my idea, my plan with this? 1 minute. This. Okay. This mini course is about at March begin of PhD level. So I introduced the problem and that I studied, and after we show some problems, open problems with this. Sorry. First, I talk about some class results with same-C surface in the Curvature spaces. After, we talk about the free boundary same-C. Same-C means covert mean constant, okay? And I talk about two minimum hypersurface surface in the ball. Next, we will talk about gap results and the stability results in the free boundary problem. After, we talk a little about index and about the Steklov 8-value problems. And what more? I talk a little about some characterization of the critical catenoid. And the last point is about some open problems with these topics, okay? So these are, in my opinion, this topic is very beautiful, but these open problems are very difficult for me. Okay, let's begin. What's my plan? Okay, my plan in this lecture 1, I give some brief motivation to study different geometry. So I remember some basic facts that normally you see, and for example, in the master course. After you give the second lecture, I will give some talk about free boundary minimum or same-C surface, especially I talk about gap results, okay? And the last lecture I will talk about free boundary same-C hypersurface surface in the ball, especially I will talk about stability. And the last one I will talk about some characterization of the critical catenoid. Especially, I'll talk about index and some results about the 8-value Steklov problem. Okay, this is my plan for our course. Okay, let's begin. In this lecture, I give some motivation to study different geometry. So, as I said before, it's very simple today, but I think that's important to talk this, especially if we have some students, master students, and see this. Okay. What's the plan with this lecture? In this lecture, I give some introduction and motivation to study different geometry. After, we talk about minimal and semi-C surface, and finally we'll talk about stability results. Remember, all these topics, we talk about the classical result, okay? In this moment, I don't talk about free boundary results. If I have time, I talk about the free boundary results today, okay? Somebody has any question or all clear? Do you listen well? Yes? Yes?
Yes.
Okay. If you have any problem, please tell me. And let's begin to talk about a little about different geometries. And to study different geometries, and it's important to say about Gauss, of course, is very important mathematician, and Riemann, this people is very important for us. After this, I remember a classical result with his parametric problem, where you have a closed curves, simple closed curves, and the question is, you have a curve, and you have this region, okay? And this curve is simple. What does mean simple? Does mean simple, for example, this curve is simple, but this another curve is not simple because you have here an intersection, okay? You don't think about this. I think about this. What's this problem? This problem is you have here a curve, and you can calculate the length of the curve, and you can ask about how do you can put this curve in the plane, in the space, that this curve is best, they occupy the best area. What does mean? You can show that the length of the curves square minus my affirmation for pi is, that's mean area is bigger than 0, okay? So the equality occurs if, only if, the curves is a circle. Okay? These are classical results of parametric problem and very beautiful problem. Okay. Now, I'll talk a little about the Gauss application. Okay. Do you remember you have a surface? You have a surface. All my surface here in this talk is regular surface, okay? And for each point here on surface, you can define a normal vector. Here, in this point, you can define a normal vector. And of course, you can define here a tangent plane in each point. And you can define application that this application goes to surface to the sphere. What I can do this? You take this vector and you translate this vector. My sphere is very big. You can translate this vector to the sphere. Sorry. Okay. This application is called the Gauss application. Why this application is very important? Because you have here the application goes to surface, to the sphere, and if you translate this, you of course the plane, tangent plane here is parallel to the tangent plane here. So you can identify this operator, differential operator, in these two spaces defined here. Why this important? This important because this operator here is self-adjoint, so it is important for us. And you can consider orthonormal basis that you can define in each point minus kappa 1 L1, and this operating in the other vector minus kappa 2 L2. What does mean? This kappa 1 and kappa 2, we call this curvature, principal curvature. So you can define two curvature that is very important for us in this mini course. The first curvature is the Gaussian curvature. Remember that, Gaussian, okay? The first one is Gaussian curvature. I will, 1 minute, I will write here. Remember, the Gaussian curvature is defined by this expression, or you can see this by product with this curvature, and the mean curvature is defined for this expression. In this mini course, this curvature is very special for us, okay? Mean curvature. So, some examples given for you. The simplest example that you can see, more simple, is the plane. Example, plane. Of course, the normal is constant. So you can see that the normal, the operator is equal to 0. And this implies that kappa 1 and kappa 2 is 0. In particular, you have the Gaussian curvature is equal to 0, and the mean curvature is equal to 0. Okay? The last example, the another example, remember, 1 minute. Another example, if you consider the cylinder, okay, and you can see here the kappa 1 equal to 0, because you have here this line has curvature equal to 0, and the other curvature is given by the curvature with the circle. For example, if you have here R, the curvature is equal by this. So you have this curvature is equal to 0, and mean curvature, is given by this expression. Okay? And the another example, very simple too, as the sphere. Very simple. In this case, you have, for example, you can consider the application, the parameterization given by this expression. So this operator, this is given by this expression, identity. And in this case, you have the Gaussian curvature is given by this expression. And the mean curvature is given by this expression. Awesome. So here you have some simple examples, okay? Only to show special to students. Okay, but you can define this expression with geometric point division. How do you do this? Imagine you have here a surface. Here I have a surface. Each point on surface, you can define it a tangent plane, okay? Here, a tangent plane. So you have the tangent plane, you can define here a vector, normal vector, okay? Then you can define what more? With this normal vector, you can define a family of planes that intersect to the surface. You can move the surface, you have a family of curves, and which these curves you can show the small curvature with this curve and the biggest curvature. The smallest Cap1 and the biggest Cap2. So you can see the another point, the same thing. And the two examples here, you can see about the example about illustrate this Gaussian curvature. For example, in the first, you have here the Gaussian curvature is negative. In the second example, you have the Gauss curvature here is 0. And the third example here, you have the Gauss curvature is positive. Okay, only to illustrate these examples. What more example you can show for you? This example here, with these images, you can here on the left, this, you have a mean curvature, and in the right here, you have the Gaussian curvature. But what does mean this color? This color red is where the curvature is positive, and you have the interpolations to positive to negative, this color blue. In the same way here in the left, you have a positive is represented by color red, and you go to blue color is negative, okay? There are some questions at the moment. Anybody? No? Let me see. No? Okay. Okay, let's continue. So now I talk a little about topology, okay? Because topology is very important for us. Remember, different geometry uses many types of areas. For example, PDs, analysis, complex analysis, topology, algebra, so many things to study this. So here I have some basic facts about topology. Imagine you have here a surface. I will draw a surface here. And this topology is the same that the sphere. Okay? But the next surface here, you have this surface, but this surface is the same topology, is the same that the torus. How do you build this? Okay. I show, especially for the students, how to build this. 1 minute. For example, you have the sphere. We have here the sphere. And you retry 2 disks, okay? We retry 2 disks and put here a handle. When you put here a handle, this is the same topology, the same the torus. This is the same the torus. Okay? And you can construct you can build another, for example, B-torus. How do you do this? You can remove two disks here and put here another handle, okay? Okay. Why this is important for us? I will tell you in a few minutes. Imagine you have a surface, you can, on the surface, compact surface, you can do the triangulation of the surface. What does it mean? Here in this picture, what you can see? Here in this picture, you have a triangulation, you have edges, okay? You have a facing, and you have the vertex. You know that the area characteristics is given by this expression, and moreover, the oil characteristic is given by this expression. Why this is important for us? This is important for us because this expression is a variant topology. Okay? What does it mean? Does mean that, 1 minute, if you have here this situation here, and put, for example, another triangle, if it is a triangulation, you can calculate this expression and don't have a change, okay? But you can more. For example, in the case where I see the sphere, you can calculate this very simple, right? You can calculate the characteristic, all the characteristics too. If in the case the torus, you have here the all the characteristics 0, and you have the calculate the B torus, all the characteristics -2. Okay. Okay, let's continue. These are basic facts. So now I give for you some examples about no compact surface. The first one is most simple, the simplest, that is the plane. And the other example is the cylinder. Yeah, very simple. And you can, beautiful surface, you can see this is no compact, okay? These are revolution surface, okay? Let me see a little about this. For example, imagine you have here revolution surface. Imagine you have here a curve, and you can do a revolution here. You have a revolution surface. For example, these are an example with a revolution surface. And remember, when I defined the Gaussian curvature, these are important for geometry, and you define too the Euler characteristic, okay? But the Gauss-Bonnet theorem say if you have integrated the Gaussian curvature, you have a point, you have married with geometry and the topology. This is very beautiful results. Here in this picture, you can see this picture, you can see here the guy with the characteristic in here, and the woman with the Gauss curvature, okay? So this theorem for us is very important because you have in the right, you have a topological results, and the left, you have a geometric results, okay? You can see this in this book. Okay, so now I will give for you about a little about talk about the mean curvature, but it's special about more functional, that these are defined by Yumori, in 1965, Mori began to study about the functional defined compact surfaces in three-Euclidean space. I will put here this functional because it's very important for us. And this function, I will put here. Remember, A is mean curvature. Okay? And this function is an invariant on the conformal transformations of the three-Euclidean space. What does mean? For example, invariant by translation, by rotation, by reflection, all this. Okay? And this function, contributes to energies of the cell membranes. What more? Mori provide that this energy satisfy this equality, and the equality hold if only if the surface is a radial sphere. Now, I'll give for you a brief proof about this fact. Okay, 1 minute. To prove these results. I remember some facts. For example, I remember that I defined here the Gaussian curvature is given by this expression. And the mean curvature is given by this expression, remember? And the Mori is given by this expression. So we can do what I can do. A simple calculation, you can show that this expression you can see here the Gaussian curvature, yeah? But I remember a simple fact that you have two numbers. You always have this inequality, and they hold this equality only if A is equal to B. Remember that, okay? So now you can consider here, by this fact here, you have it. You can use this inequality here. So you have that, in fact, this bigger or equal to 2 kappa 1 kappa 2 plus 2 kappa 1 kappa 2. And so these are the Gaussian curvature. Okay? This is very simple to show. Now, what I can do? Define the set. The set is a point in the surface M, so that the Gaussian curvature is bigger or equal to 0. Okay? So now you can see this expression. This of course bigger or equal to this expression. I forget here the area elements, okay? But this expression now is bigger than this expression. Why this? Because I have proved this, okay? So in this moment here, I remember that when I begin this mini course, I define for you the Gaussian application, and in here, this expression is the same that I will delete this 1 minute. It's the same that the determinant differential of the normal application, okay? And this is the same for pi. Why this for pi? These are area of the sphere, because here you have calculated in the set, when the set you have the Gaussian curvature is bigger than 0, and you can show that the Gaussian, the application, Gaussian application cover all the sphere, okay? So you have this. So, and you have improved finally you have improved here, these results. But what's happening in the equality, okay? So I will remember that, I will delete this. When I use this, I use an equality and say, then equality occur if only if the numbers are equal. So in this case, if the equality occurs, that means that kappa 1 is equal kappa 2. So in this case, you have the surface is umbilical. What does mean umbilical? That means that all points in surfaces, the principal curvature are equal. Okay? But how do you do now to say that this surface is around the sphere? Now you remember that I will delete this. If you have a surface, compact surface, I will do some picture here to motivate this. Remember, these are good exercises for students. You have a compact surface. My claim is exists a point on surface so that in this point the Gaussian curvature is bigger than 0, and you finish the proof. Okay, how do you prove that? If the surface is compact, you can choose a big sphere and draw this a big sphere, and you can decrease the radius with the sphere, and this sphere at some point will take it like this. And okay, what do you do here? In this point here, what can you see? You can compare now the two curvature. In this point here, the curvature with the surface in this point is bigger than the curvature in the sphere. That is the same that this expression. So you have this is bigger than 0. Okay, you finish. So there you have a surface, umbilical surface, and you have, for example, compact surface. You have that these are simple example to show that this is a sphere. If you don't have, for example, compact, you can show that is a piece of plane. Okay, so these are results, and I finished the proof. There is some question at the moment. No? Yes? All clear? Yes? Okay. Now, important to talk here, to say that Professor Fernando Codar and Professor Andrade write a very beautiful survey about the Murray conjecture, and I will talk better after a few minutes, okay? You can see this better here in this paper. And what these results prove? Humor showed that the rounded sphere have the least possible humor energy among all compact surfaces in 3 sphere. Okay, this is important to observe. Now, after humor checked that the functional satisfies this inequality, insert the class of torus, and the equalities are archived by torus with revolution, and like this, okay? But he did a conjecture, this humor conjecture, this very famous. This conjecture is 1965. What this? Every compact surface with Gen 1 in the Euclidean space satisfies this expression. Okay. There are a long history about this conjecture, partial answers, but in 2030, Fernando Condamarques and Andrade Neves provided this conjecture and the very beautiful results, of course, and in particular, they using about minimal surface in this proof, and among other results, very strong results. Okay, and now I talk with you about a little about minimum and the constant mean curvature surface. Let me see. And as I told you, this first class is lecture is very basic because I think about the student. If you have some question, please let me know. If you have some question, if my sound is not good, tell me for me. Okay. Okay, let's go to start with this. First, I talk with you about the problem with this. Imagine here, I have this problem is characterized by a variation problem. And imagine you have a surface. You can see here a surface. I will draw for you a little here, the blackboard. And you have here a surface. And each point on surface, you can define the normal vector. And you can move the surface and it can do some variation this for surface and characterize here like this definition. So in this case here, you can, this letter F is a function with a compact support in the surface M. And you can define here. What's the idea here? The idea here is can define a functional, and you can study the critical points of this functional, okay? And what I do? I do to classify the surface. Yes, this I do. Let's move on. You can define here this area of function given by this expression. Remember, this is important for us here. My surface here is compact without boundary, okay? Don't have boundary here. So you can calculate the first derivatives of this, and you have this expression. This expression said me what? This expression said me that you have a critical point, okay, for all function in this set, if only if the surface is minimal, okay, the mean curvature is gone to 0. So you have here a variation of this function, and you have characterized this surface with these critical points. A little more. Now you can see more. Here I talk about a classic problem of course. These all people here said one time this picture because it's very beautiful, very interesting picture. This picture, what does mean? These are famous problem proposed by Plateau, which consists to find a surface with the least area building and they give Jordan curve. This problem was solved for Euclidean space independently by Douglas and Hadon. What does mean these problems? If you have a curve, you have here a curve, you can meet a minimal surface that pass here in this curve. Okay, these are famous Plateau problem. And Plateau did a lot, experiment with films. Okay, these are very beautiful results. You can see this image in these homes in this site here. Okay, let me give you 1 minute. I need water. 1 minute, please. Is there any question at the moment? No? Yes? No? Okay, let's move on. What more I can? Now I show for you some examples of minimal surface, the classical example about minimal surface. The first one, let me see here, is the plane, is the most simple, is the simplest example. The another example is the catenoid. It's very important for us. Remember that when I begin this mini course, I defined the revolution surface, and the catenoid is a revolution surface. Yes, you can see here. Let me see to draw. You take a catenary, and you can move this here. You have you have here a catenoid. In this lecture, the catenoid is important because it is a minimal surface, and what more can do? There is a classification theorem. If M is a complete minimal surface of revolution, then the surface is a plane or a catenoid, only this. Then this theorem is very important when you have this type of theorem because you have here classification of surface. So in this moment here in the history about minimal surface, the only knows minimal surface is a plane, a catenoid, and another surface that knows is a helicoid. But after in the history, you can ask what more surface you can do. Okay, these are about history about minimal surface. So this helicoid surface is very beautiful surface, and you can see this image in this side. So there is a classification theorem, and the Mixi-Rosenberg provided this. If M is embedded, simply connect minimum surface, then M is a sphere or a helicoid. So you have a beautiful result about classification theorem. And what more? Now, let me talk about the cost surface. Is very beautiful and important surface that discovered by Celso Costa, Brazilian geometry, that he proved that this surface is a minimal surface, and there is a long history about this surface, but I will tell something important about this. But I suggest that you read a little more and more about this surface because it's very beautiful, the history. So this surface is this mountain. I said before, I told you that only has knows a plane, a catenoid, and what more? Helicoid. So Costa provides the surface is a minimal surface, and there are some properties very important for us. Here you can see another images about this surface, and after Hoffman mix to research, provide some results if you use the computer graphic computers, and to prove some results with this, and another picture with this Costa Hoffman mix surface. So very beautiful surface and important for surface. Okay, now I show for you another surface, minimal surface, but this surface does not embed. These are an episurface, and then another an episurface with more symmetries, and these are another an episurface, and then these are George mix surface, and this another George mix surface, very beautiful, and these are Riemann surface. If you can see more example about minimal surfaces or other things, you can visit this page. It's very beautiful. You can see another surface and the beautiful result here. Okay. In this moment here, you have some problem? No? You have some question? Let me see. No. Okay, if you have no question at the moment, now I begin the next topic. Now I talk about some examples of CMC surface. Okay. Are you 1 minute, please? What's examples in this moment you know about this with this mini course? The first example that you give here, the first one that I show for you is the sphere, remember? And I show for you too the silent buffs has CMC curvature. So, and here this picture shows that is exactly the sphere, but the another picture is the cylinder, and another picture is as before I said for you, these are beautiful revolution surface, and what more? Now I will talk about some classification theorems. It's very beautiful classification. So this theorem's classification is very important. Imagine you have here Gelé show classification theorem about the surface, CMC surface in the three-Euclidean tree space. Imagine here you have a surface, okay, and you have what does mean star shape? First, I will talk about this hypothesis. What does mean star shape? This star shape, that means you have, for example, a center. You take a line here, you only intersect the surface at one point, okay, only this. Then Gelé showed that closed star shape CMC surface in the Euclidean tree space is around the sphere, okay? These are 1953, in 1953. Okay, after Hoff, in 1956, and they proved that any closed image. Now, when I talk here closed, that's mean compact with without boundary, okay? In this lecture, in this moment here, this means that. And a closed mass semi-C topological to a sphere in Euclidean spaces around the sphere. Okay, these are famous results about Hoff. And the natural question here is, you can remove this hypothesis here. You can remove topology to a sphere. What does mean? Remember when I talk here about some important facts about topology, you can show that the characteristics, all the characteristics in the sphere, you can calculate this, then you can, I not. Hoff ask if I can remove this hypothesis here, okay? So these are famous conjectures, these are conjecture Hoff. And the Hoff conjecture that the condition of topology to a sphere can be removed. So Alexandrov provided this result with the hypothesis. And if you consider here, the surface is bound and enclosed the same C surface in the Euclidean space, then they provide that the surface around the sphere, okay? But they put here this, the hypothesis and binding. What does mean bind? Basically, the surface don't intersect, okay? And after some years, his young construct a semi-C topological and 3C in the Euclidean space that these are not around the sphere, okay? Let's move on. So in this moment here, I show for you some results about the stability of semi-C or minimal surface. In this moment here, it is important to say that all this result here is a compact surface without boundary, okay? These are classic results, not about phi boundary. I don't speak nothing about phi boundary in this moment, okay? Okay, let me see. So this picture is very beautiful. Of course, you can play this with this can do this after, and you can see here. Okay, this so here you can see. Oh, sorry, I don't know what's happening. 1 minute. 1 minute. Okay. Okay, sorry. And you can see here this picture, and what I can't classify surface with mean curvature, constant mean curvature, and the compact surface. Okay, but you need some results. Now we remember some classic isoparammetric problem. Yes. Remember that the question among all the surface in the Euclidean space that bound a given volume, and what is the surface with the smallest area? Okay. For example, in this case here, you have this surface, and you have the volume in this surface, and you can say this surface is the best. I don't know. And in fact, Schwarz provide that this best surface is the sphere. After, remember, you can ask about what are the compact surface without boundary with the mean curvature is constant. Okay. Then you remember that about a little, I speak this a few minutes before about the conjecture of, then you can see that Prof provide the sphere is the only compact MC surface with general 0. I told you, familiars. And Alexandrov provided this result about if you can consider the hypothesis embedded. Okay. So, but in 1984, João Lucas Barbosa and Manfredo do Carmo provided the following results. Okay. And what's the results? This result is about classifying all the surface, in this case here, I put here hypersurface. Let me talk about this a minute. Okay. At this moment, all that I talk with you is about surface, but now, especially to students, and I talk about this. You have, at the moment, you have here classify a surface in the Euclidean space, but I think that you have a hypersurface. In this case here, n is 2, okay? But here you have a condition is 1, okay? These are the same way that you see before, but you have now hypersurface. In this case here, Barbosa do Carmo showed that the following results. If you have M is a compact oriented n-manifold, and you have be a mesh with a mean curvature. Remember, the mean curvature is constant, but no different from 0. And they prove that if then you have this stable, only if the image by M is a round sphere. So in this moment here, what this mean stable? This hypothesis here, these results talking about stable. Now I need to speak more about this stable, then I prove these results. And in this moment here, important to say that when show the existence of a compact surface immersed in two-Euclidean space with a CMC, and that has the topology of a torus, thus provide a counterexample to Hopf conjecture. So these are important to say here. 1 minute, I will drink a water. There are some questions here at this moment. Sorry. Any question? No? Nothing? Okay. So let's continue. So in this moment here, I need to tell you what does mean stable. These are new words that I need to define here. And before, you remember that is Young and he collaborated, showed that give example of compact, no spherical CMC hypersurface embedded in Euclidean space. And of course, these hypersurfaces and events example are not stable by Theorem of Barbosa do Carmo. Okay, so you have these two observations that are important for us. Let's continue. So remember when I told you defining the minimum surface is MC surface, I talked with you about critical point, and the critical point, in this case here you have if M is a minimal MC surface, then you show for you that M is a critical point of the functional area. Remember that I proved no, but I tell you this. And this picture here, you remember you have here on the left, a local minimum. Sorry, again. I give you a minute here. Sorry. Okay. And you have here a picture that showed some example about this problem. So in the left here, you have a local minimum, and in the middle here, you have a local maximum, and the right, you can see the saddle point. Okay, these are some examples. Okay, now to talk about stability, you need to calculate the second variation of Theorem, and you can prove that this expression is very important for us. And I put here this expression because after some minutes I will use this expression. Okay, and remember what I want to classify surface. So first, I show for you is a critical point if only if, for example, which is the mean curvature is constant, but you have another hypothesis, and then now you can prove that the second variation of area is given by this expression. This expression is very important for us. I will explain all this expression. If I forget this, sorry, but sometimes I forget this, okay? But don't worry. And this expression is a bilinear symmetric, okay, symmetric bilinear quadratic. And this is a Laplacian calculated on surface. And this expression here is given by this expression. In this case, okay, remember that kappa 1, kappa 2 are the principal curvature, okay? This expression in this moment here, this, because the surface is massed in Euclidean space, okay? So, and what more you can do? And now I can define the surface is called stable if the second variation of area is bigger or equal to 0. So I said that S is stable. Remember, if the second variation of area is bigger or equal to 0. This is important for us. So, but you have more. You have that the integral of the function f under the surface. Sorry, here is very, I will put here. And the same that here. What does mean this expression? Does mean basically the volume is constant. This expression means that. So you have this interpretation here, and now I will give for you I will talk about the Barbosa-do Carmo theorem, and I will give the proof about this. Okay. So in this case here, I prove in the case about the surface, but you can the same way you prove about the hypersurface. Okay. Is there some question? There's some question in this moment? No? Yes? No? Okay. So let's move on. So, in fact, I will prove these results. and Theorem and Barbosa do Carmo. These are very, very beautiful results. In my opinion, these are very beautiful results provided by Barbosa and do Carmo in 1984. And what's the result is the following. You consider the surface a compact oriented surface, and consider a mesh where in the Euclidean space with a non-zero constant mean curvature. Then you have, if the immersion is stable, then you have that the immersion with a sphere is around the sphere until Euclidean space. So very beautiful result, classification results. Let me see. Of course, there are another result with not more with Euclidean space, but you can define this result in another space. But in this mini course now, in this moment, I talk only about this, okay? Only to give some information more. Okay, how do you prove this? Do you remember that I said before this result, the Manfredo and the Barbosa provide the result in the hypersurface, but in this moment here I'm only proving the surface in the case of surface. Okay, so to provide this surface, you can use it. I need some results. The first one results that you provide here, I put here in the blackboard because I need these results after. And then you have the first result is I put here because I will need for prove this. Imagine you have a surface mass in the Euclidean space, and you have a CMC, okay? And you can calculate that Laplacian in this function, and the letter n, remember that the letter m is normal vector, and you have here, you can calculate this, not difficult to show that, is equal to this expression. H is a mean curvature, and that is this expression. I will tell you some observation here, this expression, when you calculate here in the Euclidean space, but you have in another space, is a little different, okay? Now, the another that I need in this point here, and if you have the surface in Euclidean space, you can calculate this expression. You can see my letter here or not. There is okay. Okay. Okay, this expression is given by, if you calculate this, you can see that, sorry, you have a mean curvature and this. And the another important thing that you use here is about if you have X in Euclidean space, a surface, compact, and umbilical. Remember that what does mean umbilical? Umbilical, that means the principal curvature is equal. Then you have that the surface is a round sphere. Okay. So you have three results. What's the idea? I show for you idea, then I prove all that. Okay. What I can do? I show for you. I tell for you the idea. The idea is the following. First, if a surface is stable, after I prove with details, then you have that the second variation satisfy this. And remember, when you define this and you define stable, you need to follow the function f that satisfies this. This function is called the test function, okay? So you need to meet this function. After, you can prove that the second variation of area is satisfied that. And in this case, here you have the equality. And what I will prove? I will prove that if you have the equality, with this, you have that the second variation in the zero is equal to 0. And I will prove that this occurs only if kappa 1 is equal to kappa 2. What does mean? Does mean that surface is umbilical. In the case of surface is compact and umbilical, have that the surface is umbilical is a sphere. Okay, this idea. But I will prove it for you all detail now. Is there some question? Nothing? Okay. I will some minutes. If my letter here in Blackboard is not good, tell me please, because if you don't see well, tell me. I can write it bigger. Okay. So let's prove the results. Theorem Barbosa and do Carmo. Let's sigma a surface immersed into Curvature spacing, CIMC. When I say CIMC, is a difference of 0 and orientable, stable. Very important. Then what they proved? They proved that there's around the sphere. Okay, let's prove that. First, as I said before, you need to meet the test function. Okay, remember that in this lemma that I put here, but I don't provide, but it's not difficult. You can prove this, not difficult. And if you see here, you have when you calculate this expression, you have this. I will put here this expression. I called it only by this letter because it's more simple that for me writing. So I define this for this letter. So when you integrate this on surface, you have this equal to 0 because you don't have a border. Then these are the first one expression. So you have here this function is the integral, and this function under the surface is going to 0. So this function here is our test function. So you can only to remember, if you have a test function, you can calculate, you can use a hypothesis that a surface is stable and calculate a little more. Moreover, with this expression here, this is important for us. you can calculate this. In the same way, when you calculate this on the surface, this expression. I will put here because I will need this after some minutes. So because this surface is without boundary, this expression is equal to 0. So remember this expression. Okay. One expression and another expression that before I will use. Okay. I will delete this. And what more? Now you can calculate the second variation of area. Remember, this expression is given by that. I forget this, the area. And remember that the function f is given by this expression that I said before. And you can show that. I will put here in the slide, is better. So these all things that here you put here, and I calculate for you. Then you can do here. You put here the function f is given by this expression, so you can calculate this. After you can calculate the Laplacian of this function is this expression, and after some calculate here, you give this expression. So to prove that, use that the function f is equal to 0, and you prove that this integral of this function here is equal to 0. You need this to prove that. What this expression give me? 1 minute to write here. This expression say me that I have this. This less equal to 0, but you know that you have this expression is bigger than 2 the mean curvature square, and the equality occurs if only if the surface is umbilical. Okay. You can prove this. It's not difficult. What does mean this? Remember that the mean curvature is the trace of this operator. So you can prove this. And only observation, especially for the students, you can prove more. If you have an operator, for example, in this case here, you have a dimension n equal to 2, but you have a dimension n, then you can prove that exercise. Suppose that you have a dimension n, here M is a manifold, and prove that in this case it satisfies this condition. Okay, and the same way, but in this case you have n here. Okay, and let's move on. So in this case here, what I have that the second variation of area is less than or equal to 0, but you have it by hypothesis that my surface is stable. What's that mean? That means that the second variation of area is bigger or equal to 0. Okay, so you have that second variation of area is bigger or equal to 0, and I said before, I proved that this happened. So you have here this is equal to 0. In this case, you have here the equality. Then you see here, if you have the equality occur, then the surface is umbilical, okay? But remember that the surface is compact. If the surface is compact and umbilical, as said before, when I begin the mini course, the surface is around the sphere, okay? So in this case, you finish this proof, okay? So there is some question this moment here. Anybody? No? Okay. So these are some important introduction, I think. I think that's some introduction about different geometry, the classical results, and about CMC, surface, minimal surface, in doubt boundary, okay? Now, I will show for you some results. I begin, in fact, the mini course about free boundary, okay? 1 minute to drink water. So, let me clean the blackboard. Let's move on. So, as said before, I put these first results because I think that this course is think about the master students. So I think that it's important to tell something about these topics for master students, maybe PhD students. Okay. Now, in a few minutes, I will talk with you about free boundary semi-C surface in the ball. These are very beautiful for me. It's very beautiful topics. And first, I give for you the definition, and after I talk a little more about this. So the first, I consider here the problem, the ball, okay? You have here surface, here you have an immersion and a surface in the ball, Euclidean tree ball. What do I mean Euclidean tree ball? Remember, I put here some definition, okay? Euclidean tree ball is a set with points. And let me 1 minute to write better. X3 in the Euclidean tree space, so that the norm is less equal to 1. This is a Euclidean tree ball. When I talk about this, I will talk about this space. In this moment, this ball lives in the Euclidean tree spacing, Euclidean tree spacing, and I consider here a immersion that surface through leaving the Euclidean ball, tree spacing. What more? The sigma is a smooth, compact surface, so that the surface, I will draw some picture for you. Some intersect this is equal to boundary. When you write this is a boundary of surface. What does mean? Does mean the boundary with the ball is equal the sphere, Euclidean tree sphere. What does mean? As a set with these points in a Curvature space so that we satisfy this. Okay? Only the first to define what does mean this. Now we can define sigma is a free boundary semi-C surface if sigma has mean curvature constant is the same that you say sigma has mean curvature vector length constant is the same that I told you, and sigma intersect the sphere orthogonal. What does mean? Let me draw for you. Imagine you have a ball. Okay, you have a ball, and you have a surface here in the ball, sigma, and you have in each point of surface you have the normal vector, each point surface. Okay, but when you see here in the boundary, here, the boundary of the surface, okay, the boundary of surface intersect the boundary of the ball, that's the sphere. And what does mean? Here you can define the normal vector, co-normal vector. You can see this. I put this letter. And when I say that the right triangle, that's mean that the normal, sorry, why length about this. And here you put here, this angle here that's median. Okay. So this you can see this picture and analyze this. And the same way that I put here semi-C surface, you can define the same way that a minimal surface, but now you have that the mean curvature is equal to 0, okay? And another observation is that I put here that you work with a surface, but a surface in the ball, okay? But you can do the same definition with another. For example, you can think this about another some manifolds, okay? The same definition. So now you have here some examples about this. And you have here on the left, you have a piece of the Delaunay surface here. And on the right here, you have a caps of a sphere. The surface is free boundary semi-C surface. This image is by Barbosa, Cavalcante Pereira, my colleagues and friends. And these are some examples. What more? And this example here, we have a spherical cap that intersect the ball with a right triangle. And again, this image is by Barbosa, Cavalcante Pereira. And you have some more example here. In this case here, you have equatorial disk. These are disk. How do I will do some picture here. Oh, let me see. I will talk a little about this. You have here a ball, a clear ball, and you have this. You have here a plane, and you put here. Imagine you have here this coordinate system. You have X, Y, Z, okay? And when you intersect the plane with the ball, sorry for my draw, and you have here this disk, And this disk intersects the ball with a right angle. But when you have another plane, for example, if you take another plane here, for example, K, where K and K is different. Sorry, I put here this color. 1 minute. I changed this color. I think this better. I write with this color. Where K is less than 1 and K is no 0, then you have another disk here. But now, sorry for my picture, but what now? You don't have more that this angle here is right, okay? This surface here is they are finally called the capillary surface, but in this mini course, I don't talk more about that, okay? So let's talk about a little about this trivial example, but important example is an equatorial disk. So you have here a ball, you have here a plane, intersect the ball, then you have here an equatorial disk, this surface, okay? And there is important classification results about this rigid then provided by Nietzsche that say that if you have a free boundary surface in Euclidean space in the ball, and you have that, if this surface is topologically equivalent on disk, so you have that this surface is a disk. Okay, these are important result, rigid result, and I used this before. Okay, let's move on. So you have here a very important so free boundary minimal surface. I will use this picture. 1 minute here. And when I talk with you about some classic results, I talk with you about the catenoid results. And here you have a catenoid, but this catenoid intersects the boundary with the ball, intersect with angle equal is right angle, okay? But how do you meet this catenoid? You have a family of catenoid, you can show this. Remember that you have a catenary and you move this around the X, and this is a minimal surface. But of course you have here, remember here, center of the ball. And you have a family of this catenoid. When you show this catenoid so that this catenoid intersect the ball in the right angle, okay? And you can prove that you can do this. This is a free boundary minimal surface, okay? And this parameterization of free boundary minimal surface is given by this expression. And you can show that the letter K here is a unique solution with this expression here. So this catenoid, sorry for my draw, this catenoid is very important, and there are some problems if involve this catenoid, okay? And I can talk, is there some question about this at the moment? Is there a question? No? Let me see. Nothing? Okay, if don't have a question, I will talk more. And you remember that when I talk about some classic results in the Curvature space here, remember some remarks The first one is, and when we study surface in Euclidean space minimum surface, you can tell that you have a critical point if only if the mean curvature is equal to 0. The question is you can do the same thinking. You can show that you have a free boundary minimum surface, you have a critical point for this functional. Yes, you have this, and then you told you about a little more, okay? Now I talk with you about the first variation of volume of the sigma, but in this case here we consider not only the surface, but any compact k-dimensional immersive submanifold, okay? In the same way. But remember, when I define here in the classical result, when we prove that, sorry, I don't prove it, I said for you. When I talk with you this, I showed this information, but in this point here, I don't have boundary. So when I calculate the first variation here, you have to think about the boundary, okay? Because you need this. So let's begin. Consider here sigma k, a compact k-dimensional immersive submanifold, and you have the boundary of this sigma is inside of the boundary of M, and consider here, so you have in this case sigma immersive and a manifold. Remember that is a compact, but in this case here you have that the boundary is now in pi, okay? So that the boundary of this sigma inside of boundary of M. What more? Now you consider a family of deformation, and I put here a family of deformation given by this expression. And it's the same way that when I talk with you about the classical result, you can consider the family of deformation, and you can deformation the surface. After that, you can calculate the first variation. And when you can calculate the first variation, you have this expression. What does mean this expression? Okay, now I talk to you about this expression. And when I calculate this expression, we have here in the right this expression. And remember, when I talk with you, I need to draw again. Suppose that now I draw in the ball, but you can put this in only to understand better. You have here manifold, and the boundary you have, I have here the normal conormal vector, and you have that the boundary here, the surface intersect the boundary here, right angle. So you have this. Okay, what does mean? Let me explain better about this calculation here. And when you calculate the first variation of the formula, you have here, in the case of the classical result that I show for you today, and you don't have this expression here in the boundary. So because you don't have boundary in the first moment, but now you have it. So when you calculate this, after some calculation and use some information, you can show that. So 8 here, 8 is the same way that say before, is the mean curvature and of sigma in M. The letter X here is the variation vector field, and you can show that the first variation is equal to 0 if only if the submanifold is minimal, and what more? look for this expression here. You have, and this is equal to 0 if only if the submanifold, sorry, is equal to 0. And what more? This last here is equal to 0. What does mean? Does mean that the surface intersect the boundary of the M intersect orthogonally in the boundary, okay? But you can define in the same way that I explained for you in the classical result when I talk about surface in the Euclidean space and with the mean curvature constant. Remember that when I told you about this, you showed that in the classical result, you have a critical point if you have the mean curvature is constant, but you have the present volume. I said this. So in this case here, you can show analogous result is that the first variation of formula show for us that you have a critical point in the case for free boundary minimum surface, if you have this expression here. Let me see here. This expression is 0, and the other expressions here is 0 if only if, of course, you have a free boundary submanifold. Let me see in the same way that you have here in the black ball, okay? But you can see these results and a little more about some definition you can put, and now I'll talk a little more about this definition because it's very important to understand this definition for the other result that I showed for you. In this moment here, you have some question about this or not? Not a question? Any comments? Okay. And if you don't have question, comments, I will do some comments. The first one that I can show for you, the same way that I showed before, is the following results. Remember that when I talk to you about 1 minute to show this in picture here is very important for us, and there is a conjecture about this surface, and this question is, the catenoid critical is the only embodied minimum free boundary annulus and in the ball. These are famous conjecture done by Friese-Lin, 2012, and in this moment, at this moment, only has partial answer, but no total answer. Okay. After I do some remark here, the first one. Sorry, I put the letter on bigger because I think that if you write in small, you don't see better. Remark. And when you see the image free boundary in the ball, you can calculate the imagine you have here x1, x2, x3, and you can calculate that, and Laplacian with these coordinates is equal to 0 if the mean curvature equal to 0, and what more you can calculate, and you can calculate in the boundary. It's easy to see that you can calculate the boundary this satisfies this expression because the surface is free boundary. So you have now this expression here because the surface is minimal. Here, this expression is because the surface is a free boundary minimal surface. Okay, this I only point this only to motivate the next result. This problem when you study age value Stekelov problem, and there is a conjecture about this, and the conjecture about this praise share. Praising. You have a free boundary surface, minimum surface, and first only minute. When you have a function that satisfies this problem, I will put here bigger that I think that is better to read because here is very small for you. And suppose that you have a function defined on surface and this satisfies this expression. So these are called the age value Stekelov. This problem is Stekelov problem. So praising chain conjecture praising has conjectured that in the case of the free boundary, you have that sigma equal to 1. This is the question. These are very important conjecture. In fact, after they proved some result about the free boundary and free boundaries problem with free boundary and related with this problem, and then another people many mathematicians and did so many results about this. So what give some, there are some answer about this. In fact, Fraser proved that Fraser really provide that sigma is bigger equal to 1/2, and after you have that Batista provide that sigma in fact is bigger than 1/2, but at the moment you don't know the others. In fact, there are other results, but I will talk with you about this conjecture and another conjecture in the last and before. In this moment here, there are some questions. Not? Okay. I only remember that if you don't have a question, I will talk about more. Sorry. I will talk about more of some problems. And remember what I do in the next lecture. So today, for finish this lecture, remember that lecture 1, we talking, in fact, about some classic results. And I begin a little about free boundary, minimum surface and semi-C surface. And tomorrow, and then the lecture 2, I will talk with you about some gap results. Okay? And gap result is motivated by the problem if and classical problem if in the class results problem. There is some question? Nothing? Okay. If we don't have a question, I stop here. Remember, please, tomorrow, when I begin this class, when I begin the next class, remember that this definition, I will remember this definition, but, and this equivalence is very important for us, okay? I remember all that, but I will a little more fast to talk about this, okay? I will finish here. If you have a question, please let me know. Is there a question? No? If you don't have a question, I will finish here, this first lecture, and tomorrow I continue this discussion about these topics, okay? Thank you very much. Thank you. Thank you very much. See you tomorrow. Bye-bye. If you have any question, any comment, please put here, and I will read and I will talk with you. I stay here for more 5 minutes, and you have any question, you can write it, and I will talk with you. Thanks a lot for your see my discourse. Thanks. I see you tomorrow. No question? Any? Remember this, please, because I need this. This first variation of volume is very important. Okay. Thank you very much for you. See you tomorrow.